Hi everyone, welcome to 135th Stanford MedAI Group Exchange session. This week we have Zheyuan Zhang from Northwestern University here with us to talk about their work on robust medical image analysis. Zheyuan earned his bachelor's degree from Tsinghua University in 2018. During the summer of 2017, he participated in a research internship at Johns Hopkins University. From 2018 to 2025, he pursued a PhD in biomedical engineering at Northwestern University, focusing on robust medical image analysis using deep learning methods. Joanne, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions?
Yeah, I think you can just ask her if you have any questions in during the presentation.
Perfect. In that case, everyone, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Joanne.
Sure. Thank you so much for this kind introduction. And hello, everyone. Thank you for the coming. Today, I would like to talk about something about the robust medical image analysis. In today's presentation, we will talk about several algorithms designed for robust medical image analysis, including some dimensionalization work in classification and segmentation work, tasks. And most of work will be focusing on the segmentation task. And let's start. First is what is the robustness? It's kind of the resilience to different environment, scanner, patient profile, image properties, so-called distribution shift. Because nowadays we know, for example, like in the training of deep learning methods, people relies on the training set and test set. They should share a similar distribution, such that you can get accurate results on the test set. However, in the practice, particularly in the medical fields, this distribution shift between the train and test set always exists. This raises a very significant challenge for real-world deep learning application, particularly in the medical fields. For example, I think some of you guys might have heard about this several story. The most famous one is about Google's medical AI, which is super accurate in the lab environment for the fundus image analysis. But when people trying to apply this to the real-world distribution, we found that the story is totally different, and the accuracy drops very significantly when we're trying to apply to the real world. This reminds us that the distribution between the train and test sets, between the thing you have done in the lab and the real-world distribution. And there are several general methods what we can do to do the robustness. But the key principle behind the robustness method is trying to extract domain-invariant features and avoid the sharp minimum during the training, and so that the model can get a better minimum comparing with a very sharp local minimum. So there are several methods we can do to go beyond this sharp local minimum. Like the most widely used methods is like the augmentation. This is including the augmentation in the data level or in the feature level, and some methods like GAN. And there are also some training methods like the meta-learning or gradient operations. Also like some representation learnings like the domain alignment or the feature whitening. We can talk about the first work we have proposed in about 2 years ago. This is called correlated style uncertainty. So what is this work is mainly based on the style augmentation. The style augmentation is trying to take advantage of the instance-specific feature statistics, which contains a lot of informative styles characteristics to synthetic some novel domains. I think many of us might be already familiar with the style GAN methods. It's trying to manipulate the instance-specific feature statistics to synthesize different images according to the reference image's style. This work is published actually several years ago, 5 years. Oh, it's already 7 years ago. Yeah. But people find that this instance-specific feature statistics can be used also for the classification task. So In this work, we propose a correlated style uncertainty, which is a well-calibrated framework that go beyond the interpolation strategies by preserving the correlation between different feature spaces. What does it mean by maintaining the correlation between feature statics? For example, most initial work trying to use feature statics is called mixed style. The blue star means the sample coming from the original distribution, and people can do some kind of interpolations between this original sample such that they can generate some synthetic feature statics. And going beyond that, there is one word called DSU. It's called distribution style uncertainty. It's trying to go in beyond this original data distributions by adding some more simple Gaussian noise to the original samples. But the thing is that by adding the naive Gaussian noise, the added noise itself is not very will cause some kind of unstable training. This is mainly coming from that the introduced noise itself ignore the correlation between feature channels. Well, for most of classification tasks, this correlation between different channels can play a very important role in the in this kind of recognitions. And it's hard to ignore such kind of correlations. For example, here we calculated the correlations between this style mean and standard deviations, and we did conduct eigenvalue decompositions. We found that only a very limited eigenvectors will can dominate this whole distribution, which means that there is a very strong correlation between different feature statics, such that we can hardly ignore them in the training. But however, all previous work ignores such kind of correlation between different feature channels, or they are very, or just limited this style computation into a simple interpolations. The feature statics can be defined like the mean and the standard deviation value of the feature space for each sample. And in order to think about how to go beyond these simple interpolations and do this and maintain the correlation between the feature channels, what we have done is trying to propose a correlated style uncertainty. The work is conducted like this. From the intermediate levels features, we can extract the feature statistics. And from this feature statics, we can calculate the we can calculate the covariance metric from this feature distribution. And using this covariance metric, we can sample a Gaussian distribution from the independent Gaussian distribution to a correlated Gaussian distribution. And this generated Gaussian distribution will form exactly the same correlation between different channels. And after forming this correlated Gaussian distribution, we add this correlated Gaussian distribution to the original sample space. And this is conducted at the instance level. So after this instance level's augmentation, we restore this feature statics to the normalized feature. And by using this way, we can generate so-called augmented features. And these augmented features can be used for the classification task. We apply this proposed method on several datasets, and including some natural image classification like PACS, office home, and the medical pathology image, the Camilon 17 datasets. And we observe that comparing with the traditional methods, this proposed method achieve significant performance gain, and in the PCS datasets, and also in the office home, also in this pathology image detections. This dataset including the data collected from 5 different hospitals, and we can observe that the correlated style uncertainty shows its performance gain over other methods. We also apply these methods on this Duke market instance retrieval datasets, and we can observe that comparing with other methods, these methods can achieve a relatively high performance gain and relatively accurate identifications. Several ablation studies also has been conducted to investigate the inserting position and the hyperparameters and the bench size influence on the final performance. Overall, it's like inserting different blocks on of a correlated uncertainty in all position can achieve the best performance for the PACS datasets. But for other datasets, it might including other numbers might be the best. Overall, it's like trying to inserting this block in the deeper features might be better for the classification. And the influence of hyperparameters is also investigated, like the bench size and the augmentation values, like the alpha. So on the right part, we show that the distribution of this feature after applying this correlated style understanding. We found that most of features can be from the same classes can be grouped into the same places, while ignoring the they are coming from different domains. So this is kind of something we want to achieve for the generalization algorithm. But going beyond this, this is a relatively simple classification task, and going beyond this into most of my research focus is this medical segmentations. We know that in medical segmentations, this problem might be more challenging due to that we have relatively limited data. Like for the MRI data sets, we only have case samples with like 100. So this will introduce a significant issues. And here in this work, we are focusing on the pancreas study, particularly the MRI pancreas. Pancreas, why do we need to care about the pancreas? It's um it's a relatively small organ, but it's very important locating in the abdomen, where it plays a very essential role in the converting food into sugar for human body. It can help generate two types of human hormones, including glucagon and insulin. And I think most of us already know how important this two hormone is in humans' digesting system. But the segmentation of this organ itself is very important. The shape of the pancreas itself is not determined. It's a soft organ, so it might change during the time. And particularly here in the right image, we can see that this is a MRI-T2 image for the pancreas. And the structure of the cell is very complex, and the boundary is with other organs is not very clear. So it's hard to define and hard to segment in the old time. And the one of the most another challenging thing is that the public available MRI datasets is very limited. And actually, before our studies, there are no publicly available datasets available. So in this work, we proposed the first ever multi-center, multi-site pancreas segmentation algorithms. And why do we need to care about the segmentations for pancreas? The most important thing used in clinical is about the pancreas volumetric. It's like the volume of the pancreas. For example, like in the diabetes patients, particularly for the type 1 diabetes, the volume of the pancreas will be shrinkage a lot at the beginning phase of the diabetes. And if people can have an accurate value of this pancreas volume, it can help the clinical doctor to make the decision whether this is a type 1 or type 2 diabetes without do further testing. And it will be also very helpful in the classification, like the classification of some tumor gradings like IPM risk classification task. And if you don't serve this pancreas inside, you use a whole volume, then the classification algorithm, particularly when the patient sample is relatively small, will introduce a significant problem to overfitting in the whole scan. And so in this study, with RB approval, we developed a first ever multi-center, multi-site multi-center, multi-site, multi-contrast, large-scale MRI datasets, including T1 and T2 contrast. And to provide precise segmentation annotations for our collected MRI datasets, one radiologist with extensive experience in body imaging conducted the pancreas annotations using ITK-SNAP. And first, before doing any segmentation algorithm, we need to verify whether our segmentation annotation itself is accurate or not. So we conduct a inter-observer and intra-observer analysis. Inter-observer analysis, it means that we try to giving two radiologists, they will be provide annotation on the same cases. And for the intra-observers, the same radiologist will repeat their annotations at a second time after a period, after some time intervals. And we can find that for the inter-observers, we can, for these annotations, we can achieve one dice about 80 something. And for T1 and T2. And for intra-observers, we can achieve one segmentation dice about 96. This inter-observers dice is only about 90, only about 80, which means that this segmentation itself is relatively challenging. Even for two different radiologists, it might be hard for them making some decisions, get some agreement between for them. But this intra-observer confirms that this for a senior level radiologist, they can provide a consistent prediction for this organ
Okay, and I think
annotations.
we have a question from the audience. How many experts provided these masks? How many expert masks does each scan have? That's exactly the question.
Yeah. For example, for here, for every samples, have we are conducting like the data annotation is conducting like this way. There will be only one mask provided by a radiologist, and then one senior radiologist will confirm this whether this is good or not. If he thinks that boundary is not accurate, he will give it back to the junior levels radiologist and do annotations to some refinements. And for every scan, we will only have one mask.
Uh, okay, so when you are comparing inter-observer disparity, then basically the observers are different, also the exams are different.
For inter-observer studies, it's like we artificially selected 25 cases from T1 to T2, and the two radiologists they are asked
Two
to
radiologists.
provide annotation on the same cases. So
Thank you.
for these static cases, there will be two masks,
Two
but for
masks.
the whole data sets overall there is one.
Okay, thank you very much. That clears it up.
So going beyond this, talk about segmentations. I think many of us already know about these transformer structures. It provides one way to model the global information rather than local information. But the computation burden itself is relatively high. Trying to minimize this work, we introduce a linear self-attention structure. This is a relatively widely studied work trying to minimize the computation burdens by switching the order of the self-attention using different activity functions. And this linear self-attention structures by shifting this computation orders. Like in the traditional self-attention, we will calculate the product between Q and K first. But if we calculate the value between K and value for K and value first, then this metric will be this size of this metric will be a D by D metric rather than a N by N metric. So by this way we can by changing this computation orders, we can significantly reduce the computation burdens. Uh, so we use this linear self-attention structure. We combine this linear self-attention structures into the nnUNet segmentation frameworks. And this help us to enhance the conventional encoder and decoder segmentation paradigms. We apply this proposed methods on the collected pancreas sets. First study is trying to investigate for this CT data sets. Within this, because for CT we have a lot of data sets for the pancreas studies, like for the abdominal 1K, AMOS, WARS, or BTCV. We show that applying these methods in this abdominal, we train our model only on the abdominal CT1K and test this proposed model's performance on the rest of the sets, like AMOS, WARS, and BTCV. So by this way, we can observe that there is a profound impact of domain shifts when we apply a trained model. Even we have a relatively large size, like 1,000 cases, there will be still kind of shift when apply on other datasets. And this reminds us the importance of this domain shift. But overall, the performance on the CT dataset is relatively accurate, and the dice coefficient is around 80. So it can be useful for many clinical studies. And then we move to the central part of this studies, like leveraging this first time collected multi-center pancreas studies. And we conduct segmentation models on this. This is the first stage work when we train this model. We train the model, we train the data, we train on the data from the Mayo Clinic at Florida and NYU hospitals. Use this about 300 data as a training. And when testing these models, we test on the rest of the data sets like the Northwestern, AMOS, or Allegheny or MCA. And we found that for the training, we can get a dice coefficient about 85. This is one dice coefficient has never been achieved by previous research. And actually, this work can be widely used for clinical studies. And we also observe that the influence of these proposed methods on the rest of the sets like Northwestern or MCA or AMOS. And we can still observe that kind of data shifts between between the train and the test domain. And here we provide some visualizations between these samples. Similar performance can also be observed on the T2 segmentations, and we can achieve one segmentation dice about 86. And for the rest of the domain, we can still observe that it's kind of distribution shift. And here we also provide a visualization here. As we said in the beginning of this study, it's like the most important parameters the clinical people will use is about volume. So here we calculated the predicted volume from our segmentation and the ground truth segmentation provided by the clinical doctors. And we found that for most of these studies, so we will have a relatively high R2 value. And this high R2 value indicates that the accuracy of segmentation methods. And it means that we can really apply these methods on the clinical environments. And we also visualize this we visualize the domain shift between these data centers. And which means that we need to propose a more robust domain generalization algorithm such that we can make this suitable for clinical environments. And here we also derive our correlations between dice coefficient and volume prediction errors. In the previous time, most of segmentation methods will give only evaluation on this on the dice coefficient. But for some more clinical studies, clinical doctors, they care more about this volume prediction errors. Through some more mathematical, through this HME, GME inequities, we can derive the correlation between this volume prediction error and the dice coefficient. We can find that the volume prediction error itself is actually bounded by the dice coefficient. When you have relatively high dice, then the volume prediction error will be relatively small. So. But when you want to get a really accurate prediction means that your volume prediction error is relatively small. Then you need to get a very high test coefficient. And here in this derivation, so we show some kind of tools such that people can calculate roughly estimate your volume prediction error from the test coefficients. Then this tools is this research has based on this we proposed segmentation methods called PanSegNet, which includes the T1, T2 segmentations for pancreas. And here, this is one study is conducted on the imminent datasets. It's one dataset that widely has been used. This is studies for diabetic cases. And this diabetic cases study is very important in the clinical. And so actually there are about many institutes trying to validate this. This is a validated studies. They provide us 20 cases with annotations from their patients, diabetic cases. And we directly conduct an evaluation without any fine-tune or retrain. And we can observe one test coefficient about 81 and 83 for T1 and T2 respectively. And then we apply this data sets on some T1 sample, T1 and T2 pancreas diabetic cases. Furthermore, going beyond this, we also conduct a pancreas part studies. This means that the pancreas itself can be divided into three parts in terms of clinical protocols, like the head, body, and tail. And this has never been done before for this body splits, part splits. And we also provide these tools for better quantifications in the clinical environment. And all the data and code is also released publicly.
Joanne, I
Particularly,
have one question. You're building this head, body, tail segmentation on top of your um, pancreas segmentation problem, or you have like three different models coming out?
it's one model.
It's one model, and
Yeah.
like you're adding another head on top of it to define like if it is the head, body, or the tail of the pancreas.
Yes.
Okay. Okay. Thank you very much.
So actually, to facilitate more studies in the pancreas studies for the whole fields, we also provide a simple GUI software such that clinical people can use it through a simple click. Just you can just drag the data here and run this enforcement. This software has been requested and used in about 20 cases over US, so it can really help a lot in the clinical studies. And this data sets overall for this study is like the first ever multi-center multi-site MRI pancreas segmentation algorithm. And the best 3D method has been results has been achieved. All the code, data model, and label is also public available. And we also validated the model's performance under the real clinical environments. Going beyond this, focus on the robustness methods. The previous one is more like focusing on the clinical studies and dataset collections. So this one is our TMI work we published last year. We are trying to, the motivation behind this work is that in medical segmentations, the securities of high quality labeled data always be a significant problem. So we propose a novel approach to address this challenge by developing a controllable diffusion probabilistic probabilistic models with text for medical image synthesis. And for these methods, what we are trying to do is to generate augmented samples from the for segmentation task. So to do this, we need first trying to train diffusion models. But for a diffusion model, if you're trying to train from scratch, then this can hardly be used for a segmentation task because you can hardly find the pair between the segmentation label and the real and the images. So here in this study, we are trying to use edge information as a condition, serve as a promote for the control net for the diffusion models generations. By using this edge information as kind of condition, we can make sure that the generated image and the input label itself is aligned at the pixel level. So which means that we can also get the segmentation label from this at the pixel level. We first train this network on the relatively large scale radiology image dataset called RedImageNet. It contains about 1 million image pair, but it's in 2D. So as the second step, to make sure that this proposed methods can be applied for our downstream task, we apply this pre-trained model on the test-specific datasets. And this allow us to do some adaptations to unique characteristics of each dataset, like the ultrasounds or MRI or CT. And in the last step, in the real downstream task, before doing segmentation, we will first sample some space using our generated diffusion model. And then using these sample augmentations, like adding different promos, like saying that ultrasound breast enhanced contrast or the dark image, something like this, this perturbation on the time space we can generate some augmented data. And this augmented data will be randomly fusion with the original data and use this generated data into the final segmentation, like different units. Um, at the first step, after aligning this edge as a condition for this stability diffusion training, we can get an image like this. The first is the original image with its conditional text, and the second row is the edge. And the last one is our generated samples. We can find that comparing with the original one, actually there are a lot of difference between them in terms of this intensity distribution. Like here, they will introduce a very different intensity distributions comparing with this original one or here in this MRI knee or ankle. But overall, the shape of the shape of the image itself is maintained very well between the original and the augmented samples. For a classification task, this kind of generation might be harmful for the classification because you are destroying the original intensity distributions. You might lose some information. But for a segmentation algorithm, what we need is the kind of segmentation based on the structure. The structure is the most important thing. And if as long as the structure itself is accurate, then for a medical algorithm, it should be accurate in terms of the segmentation results. And it should be able to ignore such kind of intensity shift. So based on this principle, we generated several samples. And you can see that the generated sample itself, compared with the original one, is very different. And some of these patterns might even not accurate in terms of MRI devices, and in the CT or in the ultrasounds. But it maintains the very accurate structure information. So this structure integrated, and this structure integrated itself can be used for these accurate segmentations. Then we apply these generated samples on this augmented on some datasets, including the MRI, prostate MRI, and including the spleen CT and the breast cancer. We can find that comparing with the traditional data augmentation methods, these methods can lead to a significant performance gain. And particularly in this ultrasound datasets, this kind of intensity perturbations based on this diffusion methods enable us to remove a lot of false positive regions and focus more on the shape distribution of this one of the original segmentation tasks. And we validated this model's performance on different segmentation backbones, no matter the basic unit, residue unit, attention unit, or the swing unit R. We can find that this data augmentation method called DiffBoost can lead to noticeable performance improvement in the segmentation reliabilities, and to further help with the final segmentation methods, segmentation performance.
Joanne, I'm wondering here, is this method of augmentation, does it preserve the abnormalities? I mean, I can understand that it would preserve the shape of the organ because it has learned that, but what if there is a tumor? While augmenting with that, would it preserve that abnormality, or that's not the focus of this project?
Yeah. For example, if you have a specific tumor regions,
Mhm.
you can serve the boundary of tumor as part of the edge promos, and this can also help you to guide that this tumor's shape. And you can
Okay.
also use this for the generations. And actually, if you want, you can even change the shape or the location of this edge of the tumor. And through this way, you can change the location of your tumor and get more samples, like growing some tumor in a healthy samples. And this can be also helpful for you to generate more samples with tumor.
That would need manipulation of the edge masks that you're providing,
Yeah,
right? Okay,
yeah.
that makes sense. Thank you.
Because only when you have the edge information, you can guarantee that the generated image has a pixel level corresponding with your problems, right?
Mhm. Okay, thank you.
And so the third work is about some adversarial attack trying to enhance the model's robustness through adversarial attack. This is a very simple and a very interesting work. Because previously we have mentioned that for a segmentation algorithm, what we want is the model is more focusing on the structure rather than the intensity. So can we design a method such that we can use a adversarial attacking way to remove the model's influence, the model's reliance on the intensity distribution rather than the to focus more on the shape? So here we design a thing called the intensity attacker. In the first step, we will calculate the influence of model's reliance on this intensity on different intensity distribution. And as a second step, we will maximize the segmentation loss, which means that we will try to manipulate the original intensity in a most toxic or a most harmful way. And after these interpolations, you can generate different samples, and this generated sample will contain different intensity distributions, but this sample will share the exactly same shape structures. Trying to do this, we need to design kind of function such that you can do an interpolation on the original samples. So here, the function will be defined like this. The reason to define this is that this function follows very good properties. First is it's monotonic increasing, and the value of itself will be bounded as 0 and 1. And if you don't do anything before this attacking, then this will be exactly same. This element will be exactly same with the original one. But after interpolation, you can change this anyhow. But this will be bounded anyhow bounded by 0 and 1, which means that the intensity value itself for the segmentation will be also bounded by 0 and 1. And using this function, we can calculate the interpolation on the original intensities, do a intensity mapping using this function. Here we show some samples after the intensity attacking. At the initial initializations, this attacking functions will be fx will be equal to x. So this will be the original samples. But after the attacking, we can find that some regions, the intensity value itself is already being manipulated. And after this in manipulations, because this is only an intensity mapping, so the shape of this organ will be still maintained. But the intensity or distribution will be totally different. And we apply these methods on some different data augmentation methods, on some different domain generalization methods. We can see that comparing with other methods, Our proposed methods can achieve a relatively significant performance gains and also impose the MRI segmentations. We further investigate the influence of different intensity mapping points and adversarial attacking intensities. It's like when your intensity attacking value is too low, then the model might be not effective enough to give a good response. But when the intensity value is too strong, then you are destroying the whole classification, whole the segmentation methods. So the performance will be also not very good. So there will be kind of selected regions such that you can get a best performance. Overall, these two methods is still fall within the traditional methods trying to enhance the robustness of medical image analysis, particularly in the segmentation task. But I think most of us already catch this trend in the last several years in terms of the large models, particularly in the clip work. Here we showed one finger from the clip papers. It's like people found that comparing with different robustness methods, one zero-shot pre-trained clip might lead to a better performance comparing with all the robustness methods, which means that the large-scale pre-training itself might be a good or a promising solution towards to address the real-world domain shift issues, particularly in the challenging clinical setups. And but however, these large-scale pre-trained models is missing for the MRI studies because there is no enough data, particularly for MRI data. So in this work, we propose a semi-supervised way to leverage some unlabeled MRI data cases such that we can train large-scale models. And for here, we will rather than use a simulation framework based on the transformer structures, here we use nnUNet structures. The reason behind this is that recent research like the Touchstone or nnUNet revisits have validated that comparing with the transformer structures, the nnUNet based training framework can achieve even better performance and fair comparison scenarios. So in this work, we modify the nnUNet architectures with different text promotes as with different kind of promotes like the text box or the points. And the current large pre-trained model for medical segmentation is mainly focusing on the CT, like the MedSam 2D or MedSam 3D or segments, where a lot of MRI data modality is actually missing due to limited annotation data. So we will use a semi-supervised way, which means that in this training scenario, labeled data will be guided to train a student models, where these student models weights will be transferred to a teacher model using the exponential moving average. And then for unlabeled volumes, we can use some artificially generated promos, like artificially select the points or the box, and use this one to conduct an inference using this teacher model, and so that we can get a pseudo labeling. And with this pseudo label, we can get the training of the student model. However, in this training process, we need to be careful because a lot of time your model might collapse when you have a relatively limited data on large unlabeled applied on the large unlabeled volumes. So we introduce the graph segmentation, which is unsupervised segmentation way. It can generate some kind of structures for MRI segmentations. It is not accurate, but it can provide some structures there. And these structures can be used to serve as a regularization. And this regularization can guide that the student model will generate some meaningful segmentation rather than some random gap, random or naive model collapse. And we test our performance on our collected MRI datasets. And here we further extended our collected datasets and split the data as such. we investigate the two kinds of domain shift. One is the domain shift between different data centers under the same data phase. And another one is between different MRI sequences. Because we know that for MRI segmentation, there are different sequences used for different disease or different purposes. And these different sequences can play one very important role. And in clinically, if we train a model only on the venous phase, can we apply this model on the outer phases? So for example, like here, the venous phase, it is widely used to detect the pancreas tumor. And outer phase can be used to some kind of fat diagnosis and characterization of the pancreatic lesions. And we collect the venous data coming from the five data centers, and we will take this MCF and OYU data, roughly 300 cases as the source domain, and test on the rest of data centers. For example, here, this is a sample coming from NU. This is the venous phase, and the right one is outer phase. From the image itself, it's very different. The contrast between the pancreas and a nearby organ is very different between these two phases. And this dataset can help to analyze the distribution shift between two different phases, which is very important in the clinical environment. But this has never been studied before. So under another thing we want to remember is that because in the old time the dimensionalization task or the robustness tasking in the medical field is slightly mass. Like some people will use the data coming from the data coming from the testing domain as part of validations for the model saving. But this one will introduce a significant bias. We can show it later. Compared with the traditional methods like different dimensionalization methods or the large segmentation models or the pre-trained medical segmentation models on abdominal 1K or total segmenters, we can find that our proposed methods can achieve a really significant performance gain compared with others. From the baseline, the death coefficient only about 40, and we can move this segmentation performance to around 70. This means that without any training on the venous phase, on this outer phase, just train the data on the venous phase, we can actually achieve one promising segmentation performance on these outer phases. And here we visualize the performance. We visualize the kind of difference between this venous phase performance and outer phase performance. So like in different segmentation methods, different dimensionalization methods, they can achieve one good performance in terms of venous phase. But when we try to apply it on the real challenging outer phases, then most of methods can hardly achieve one segmentation performance about 50. But for our cases, we can achieve one performance about 70. And in the red part, we visualize some kind of segmentation results. And we can see that comparing with others, this segmentation performance gain is really significant. Another thing we need to mention here is about the domain shift. As we can observe in this data collection, for every test data center, we manually balancing it such that every data center has relatively large validation. For every center, we will have 50 cases just for testing without anything for the training. Then we validate one problem is that whether this kind of distribution shift between different data centers, are they coming from a domain shift or coming from data leakings? For example, here, when we reduce, initially we don't have efficient data samples for the training, then the death coefficient will be very low, and the variance between these different centers will be also very high. But along with increasing the number of this source domain, we can find that this variance between different centers will be reduced very significantly. Like here, the performance will increase similarly, and the variance will be decreased very significantly. And also, if your test set, the data is relatively limited, then which means that you might even have a even higher testing variance. This indicating that a lot of variance coming from the measurement from the measurement might coming from the case level variance rather than the domain shift between different centers. So before claiming about the domain shift, we need a more solid measurements on some core centers on some core center shifts. We need to use a relatively large number of testing cases to guarantee that this one is coming from the shifting from the core center rather than shifting from the case level variance. But when we're trying to move to the different phase or different sequences, the thing is totally different. For example, when we increase the training steps, on the original testing, on the original source domain, the performance gain might be limited, but for some different domains, there might be still some kind of performance gain, like showing here. Remember for this same phase scores, they will keep increasing. But for different phases, like this auto phases settings, the dice coefficient might even drop when you increase in the training, which means that the original model might not we cannot say overfitting here, but it's like make itself more suitable for this Venus phase rather than for the general pancreas studies. So it's like the increasing training might reduce the performance on the auto phase. And another thing we can observe here is that when we increase the fine-tune blocks for during the fine-tuning stage, so we can find that for this same phases, then the performance we can also observe the performance gain. But when we move to a different phases, then the thing will be very different. The performance might even drop. So it reminds us that we need to be more careful to deal with the domain shift issues in the clinical studies. So summary of all this work, we propose a correlated style uncertainties, which is used for classification tasks. We proposed a robust segmentation methods for the correlated largest ever pancreas studies for this pancreas MRI research. And we publish all the data code for people to use. And we propose a DiffBoost method to utilizing the controllable diffusion methods for data computation, and one adversarial attacking method to enhance the robustness. But in the last method, this one is we propose a large-scale semi-supervised medical segmentation methods, and this is a strong base model for building more robust medical segmentation models. And in the future, particularly in the next few years, domain shift will be continue to extract more and more attentions in the medical fields. Because when we try to apply the deep learning methods on the real clinical setups, we will find that this domain shift will introduce more problems. And the foundational models will be keep leading trend to addressing this domain shift, because only by helping the model experience larger enough data, it can help us to build a more robust medical analysis tools to solve the real clinical problems. And our general algorithm in this since will be valuable for part of such system, because they can be served as a good baseline for anything with the new developed AI methods. This work is supported by NHR1, and thanks to my supervisor, Professor Willis Bexy, and all of my collaborators, including Mayo Clinic, Johns Hopkins, NYU, or Netherlands, USC, Indiana, or Istanbul University of School of Medicine. So thank you. Glad to answer any questions.
Thank you very much, Joanne. Thank you for this very interesting presentation. Before we move on to questions, I'd like the audience to give our speaker a virtual round of applause. And then the floor is open for questions. If somebody has any questions, please go ahead and ask.
That was very
Hey,
interesting.
I had a question about the CSU. I think in
Mm.
your architecture you talk about like mixing the style, but I guess I didn't really understand how you remove the feature statistics from the intermediate features. So if you could explain that a little bit better, that'd be great.
Yeah. Here the feature statistics is first defined by the mean value and the standard deviation values of these features at case level. For example, like for one cases and for every channels, we calculate the mean and the standard deviations. And at this step, we are split into two parts. One is the moving the feature statistics. So by moving here means that it's actually normalized. We just use the original values to remove this one, just like something we have done like the bench normalizations. Remove the mean and divide it by the standard deviations. And by remove this one, we can get all normalized features. With this normalized features, we can add the feature statistics, which is generated one, which is a synthetic feature statistics. And this synthetic feature statistics can serve as kind of augmentation for the original feature and the feature spaces.
Okay. Okay, thank you.
Yeah.
And I think Ramon has a related question. Are intermediate features coming from one single layer, or is the technique applied to all layers?
You for this feature statistics, it's coming from one layer, just like shown here. But you can inserting this at different depths, so you can apply this at the different layers.
A question about the data acquisition when you created your data set for the pancreas.
Mhm.
Is that like a traditional clinical scan for pancreas, or is there something? Is it like a special pulse sequence for scanning the pancreas?
Oh no, it's like the clinical scans.
Okay, that's great. So
Yeah.
one I really like all the work you did. So one thing you see is like you are segmenting a single organ, and even like but I think your so total segmentator released MR total segmentator in February, the radiology paper. I was
Mm.
checking their result. Um, they do really well on on liver, but
Mm-hmm.
on pancreas their performance is quite poor. Like it's
Mm.
the dice is like 0.7, right? So
Mm-hmm.
my general question is like this: a lot of people are segmenting multiple organs at the same time. So,
Mm-hmm.
they'll try to segment 40 organs from the single scan, right? But here you focus on like segmenting only one organ,
Mm-hmm.
and you do really well. And, I know like like you mentioned, like the pancreas is very small.
Mm-hmm.
So any thoughts about like segmenting big organs and small organs, and whether do they separately or do them together? Yeah.
Uh, it's actually a really good question. Like for the total segmenters, they are trying to segment a lot of things.
Hmm.
And for recent work like the SAM or the MetaSAM, they are trying to segment anything.
Right.
But in practice, people will find that, at least to me, for me, the feeling is that when we try to apply the experiments on the various organs, then the segmentation performance is not as good as a
Mm.
specific model for specific organs.
Okay.
But the thing is slightly tricky. As we showed in the last sections, we might need a large model which is trained with multi-organ as a base. But this
Mm.
base model should not be directly applied to the clinical environment. When we apply to the real clinical environment, we might to develop a specific model based on the base model. And this
I
specific
see.
model for specific organ itself can be really used for clinical setups.
I see. So like you have a base model and then maybe
Yeah,
fine tune it for.
then exactly.
Okay, thank you.
If there are no more questions, then thank you very much, Joanne. Very interesting presentation. One more round of applause for our speaker, and then we can sign off. We'll put this talk on YouTube, and if any of the audience have any questions, we can hopefully put them in touch with the author later. Thank you very much.
Thank you.